Hi, everyone. I'm Tony Aylward, and I'm going to talk to you about Rare Flora, where we're using plants to mine rare earth elements. So, uh, there's a huge market for these things that's several billion dollars globally, a couple billion dollars domestically, and even if we go for a small slice of that, it's looking at like $100 million. The way we want to do this is by extracting rare earth elements from soil with plants by a process known as phytomining. So the usual way you get rare earth elements is by an open pit mine, which is extremely expensive, time consuming, environmentally destructive, and geographically concentrated. Most of them come from China. Phytomining is our solution to this. It works by planting plants on metal rich soil, in this case, rare earth rich, having that metal brought up into the plant's above ground biomass, then harvesting the plants and processing it into what we call bio ore, a material that's very rich in those rare earths. And this avoids those downsides of open pit mining. It's much less expensive upfront. You can start a phytomining farm in months, theoretically. It's much more environmentally sustainable than an open pit mine, and especially geographically accessible. There's a range of sites in just the United States with soils that are rich in rare earths. So for a couple examples of that, we're working with collaborators at the University of Idaho and University of Nevada who have their own projects targeting rare earth soils. And they also have methodologies in place to extract metals from plant biomass. What they're missing is the perfect plant to do this with. So if we look at our collaborators in Idaho, where they're working with soil from the Diamond Creek project here, that is up to 3% rare earths by weight, they've, in collaboration with us, identified a good candidate, in fact, a couple of plant that can grow on this soil and take metal into its stems and leaves. The only missing piece to make this an economical system you can get rare earths out of is to enhance the rate of metal uptake into the plant. So like just get a little more metal in that above ground biomass. And that's what we're doing at Rare Flora by a couple of methods, either by treating the soil with peptides or small molecules that target the behavior of the roots, or by actually genetically engineering the plant itself. We are enhancing the uptake rate of the metal into the plant's above ground biomass. And that's what's going to create an economically viable phytomining system. The business model here is the confluence of these three stakeholders that I've discussed. Looking at our Idaho example again, we're working with the University of Idaho, who is prepared to process their biomass. They are connecting us with, Idaho Strategic Materials, who owns this rare earth rich land where the soil is. And we, Rare Flora, are setting up to be essentially the provider of the seeds and the license for the genetics for these plants that can grow on this soil and be this part of the process, ultimately to produce that bio ore and sell it into the rare earth element supply chain. So we're actually not the only company that's setting up to do phytomining and extract metal with plants. There are several others, especially in Europe. We are the only ones who are set up with collaborators to target rare earth elements. Here we are. This project got started with myself and my colleague Ying Sun when we were working at the Harnessing Plants Initiative over at the Salk Institute. And we were able to connect with some very helpful collaborators at the University of Idaho and University of Nevada, where we are spearheading these projects. And so now I guess I have a few minutes to take your questions. So thank you very much. I can
Hello.
at least.
Yep. I apologize. I was fiddling with the QR code when you started here. Can you say again what sort of the problem solution is?
Yeah. So the big problem is that so especially if you think about the technologies that are needed to have renewable energy and electric vehicles, these are very intensive in like the use of rare earth elements, mainly for permanent magnets. And the projections are that you're going to need like 10 times as much rare earths to meet either global wind power goals or US electric vehicle goals. And that's just arguably, I think, not reasonable to expect you're just going to dig more open pit mines to get that. So by employing a phytomining strategy, we can actually have a sustainable source of these critical metals, and also, like, fairly importantly, have a domestic source of them, which is why we're currently looking at places in Idaho, and our other projects are looking at places like Michigan, Minnesota. And yes, I think that is most of the answer.
So just finish off the solution part. You have these magic plants that extract the rare earths. Then what happens?
So then they go, so you have basically you harvest them, and you have the plant dry biomass, which goes into a process to convert it into what we call bio ore, either by heating it without oxygen, which is what we call pyrolysis, which is similar to the process for biochar, if anyone's familiar with that, which basically evaporates a lot of the extra material from the plant biomass out and leaves this sort of very metal rich charcoal like substance, which is what we call the bio ore, which in fact is significantly more concentrated with metals than the usual rock ore you would get out of a pit mine. And that material we expect to be able to sell into the supply chain for whatever other metal processor and supplier will be refining it to then eventually go into a permanent magnet or other application.
So I have a question. As opposed to the traditional method, how much is lost in the refinement process when you turn it from the bio?
Oh, that's a really good question. You mean, so I don't have the references to answer that right now. Are you thinking in terms of like refining the ore, or in terms
Just
of
simple, if you were to just mine it straight weight to weight, and if you were to phytomine it, and part of that phytomining process, it's being uptaken into the plant, and then you burn it, and then you refine it, and you get it out after it's being took from the plant. So how much is left versus if you just traditionally mined it?
well,
what is lost is what I'm saying.
How much metal is lost?
Yes, of the rare earth metal.
So the rare earth metals, like the reason for doing the pyrolysis process is because you're using basically the weight of the rare earth elements, and they are very heavy, to keep them in place while the rest of the material evaporates. And we don't really factor in a like very large fraction of the metal leaving during the conversion process, really, which is why we're looking at the actual plant's uptake as the limiting factor. I think based on what we're looking at in our collaborators' labs, it's a very small fraction of metal that is going to leave the pyrolysis chamber. So whatever we get into the plant, we do expect to get also into the bio ore.
And just one last point is, it's not to say that you get all of the metal in the rock itself. Like, so you would have a second pass through it after you do the phyto mining?
Yeah, this is a really important question. I would expect to have several, it's basically one crop per year, and I would expect to have several years of that. It would maybe be really awesome if we could get all of the metal out of the soil in 1 year, but I don't think we're going to have the plant that does that immediately.
All right. Thank you very much.
Thank you, everyone.